All right. What we've been talking about is we've been talking about calculating changes of functions. And one application that we've seen is motion. And so we defined a velocity, right? So you can have like a piecewise linear motion graph, okay? So, for example, x, the position is a function of time, and you can have something that is piecewise linear, and we saw the way that that worked or how to deal with that. And then from there, you can graph a slope or velocity graph, and that in this case you would have it would be piecewise constant, something like this. All right, so that's the slope graph that goes with the piecewise linear graph on the left, and that's all well and good. However, we all know that not every graph is piecewise linear. Okay, not every slope graph is piecewise constant. So we have to now talk about what happens if you have something more complicated. All right, what about something like a parabola? Let's do that below. Okay, so let's have now x of t, something that moves, that makes a position graph that is a parabola. So let's maybe x of t was equal to t squared. Okay, so what would it mean to talk about the slope of a parabola? Or what would it mean to talk about the rate of change of a parabola? Okay, so first of all, that's very complicated. In fact, it's not really even clear what that means. Okay, what we're going to do for the time being is we are simply going to approximate. We're going to deal with curves by treating them as if they were piecewise linear. Now you say, wait, hold on, how can we do that? Well, what you need to do to get an approximation is if you want a really good approximation to a curve like a parabola, you want to use lots of linear segments. So look on let me put a lot of little yellow straight segments. Can you see that if you glued together lots of tiny sticks, can you see that would turn a curve? You could approximate the curve, in this case a parabola, by a complicated piecewise linear function, right? And once we did that approximation, then finding the slope of each of those pieces, each of those sticks, is something we could do, right? Okay, so that's the gist of how we're going to handle the impossible. We're just going to use an approximation. Okay, now we've been dealing with velocity graphs that are piecewise constant. We learned about the fact that you can calculate the areas underneath them by looking at the position graph, the delta x. Okay, and we did some other stuff, but we've never seen something that wasn't piecewise constant. Okay, so what happens if somebody gives us a velocity graph that we can't use our toolbox? So let me give you something a little bit more complicated. All right, so suppose that the velocity was like the following. This is something that we all see in real life. Suppose somebody was simply slowing down. If somebody was slowing down, then the velocity would simply get smaller and smaller until it went to zero, right? Okay, so there's a velocity graph that's not piecewise constant. Okay, so how would we handle that situation? Well, once again, we could make an approximation. Okay, that ramp is not piecewise constant, but however, we could make a rough approximation by using a staircase, right? Okay. Now, once again, I know what you might be saying. You might be saying a staircase is a really terrible approximation to a line, a slanted line, right? Okay. If you need a better approximation, simply use a staircase with more steps. Okay, how about if we had 1,000,000 steps or 1,000,000,000 steps? Can you see that it's pretty soon you can't even tell the difference, right? They pretty much the red staircase would look like the slanted line. Okay, so this is how we're going to start to handle these more complex situations. Okay, and we could do this with lots of different functions besides just parabolas. Okay, like for example, let's take something that some people think is kind of complicated. Let's take a trig function. Okay, so let's say that we had a position function. Let's say we had x of t that was, let's say something was moving back and forth like a pendulum. Okay, so it went in one direction, then it went in the opposite direction, then it went in the up like this. Okay, so the position is given by the sine function. Okay, remember that from trig? Okay, so once again, that's not something that's piecewise linear, but you could approximate it with piecewise linear pieces. Okay, so we could do this. We could calculate the slopes of each of these sticks, and then we would have an approximate piecewise constant slope graph or velocity graph. So the point is this works for all kinds of different curves.